Okay, so now we covered the basics for IEEE representation, floating point representation. Let's do an addition in these formats. Just a quick reminder, let's say you have two numbers in decimal. Let's say they are at 120 times 10 squared, and you want to add 315 times 10 to the first power. Obviously, this is not as simple as adding 315 to 120 because the power of this 10 and this 10 are not the same. So you have to make sure that they are before you can perform the addition. So this is basically 120 times 10, and you bring a 0 here. So this is 1200 times 10 to the first power plus 315 times 10 to the first power. Now you can add these two numbers and get the result. So same thing goes basically for IEEE representation. When we're adding two numbers, we have to pay attention to the power that the exponent basically before we can add the mantija together. So let's take an example. Let's say I have the first number 0 1 0 0 0 0 0 1 1 1 1 0 0 0 0 0 0 0 0 0 0. Let's see how many. Do I have enough zeros here? I need one more set of zeros. Okay, and I want to add it to the following number. One, 0 0. Okay, so let's convert the first number to decimal and the second one to decimal and see what needs to be done before we can actually add them. All right, so for the first number, I have 1.11000, and then like a lot of zeros, okay, times 2 to the power of this exponent, which is 131 minus 127, which is 4. And then the second number is 1.010000, and then again a lot of zeros times 2 to the power of this exponent minus 127. So this exponent is 130. 130 minus 127 is 3. Now obviously I can't add them right away like this. I have to make sure that the exponent of this 2 and the exponent of this 2 are the same. You can either move or convert this to 2 to the power of 3 by moving the decimal, the radix point to the right, or make this one times 2 to the power of 4 and by moving the radix point accordingly, right? Okay, so either way, you're going to get the right answer. It doesn't matter. So so let's say I want to play with this number. So I'm going to take this number and convert it to 0.10100000000 times 2 to the power of 4. Now I can actually add this number to this number. So this becomes, I'm going to just write them down here, 1.1100. That's actually enough zeros for now. The other number is 0.1010. Both are times 2 to the power of 4. If you add them, you get 0, 1, 1, 0, carry 1. 1 plus 1 is 0, carry 1, 1. Here, and the period or the radix point is here, times 2 to the power of 4. Now, obviously, I can't store this back into IEEE representation because it's not normalized. So I actually have to normalize the number first. Okay, so now I am going to normalize it. So I move this one here. So this becomes 1.00110 times 2 to the power of 5. Now, in order for me to save it into IEEE format, I have to basically, I'll drop this one, this becomes my Manteja, and then I have to add 127 to that power. So this becomes, the sign bit is still 0, nothing has changed, we're adding two positive numbers, so the sign will continue to be positive. And the exponent has 8 bits, so this is, the exponent is going to be 132 in this case, and I have 1, 2, 3, 4, 5, 6, 7, 8. So 132 is basically 128 plus 4. I'm just trying to decode it into binary. So 0, 0, 1, that's my 4. And then this is 0, 1, 2, 3, 4, 5, 6, 7. So it's 128 plus 4. So that's my exponent. And then the Manteja bits. Dot, 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 dot. So my Manteja will be written here. Okay, and this is the result of adding the previous two numbers in IEEE format. Similarly, if you have two numbers that you need to subtract, you follow the same steps. You just basically have the exponents to be the same before you perform the addition or the subtraction. I mean, the principle is pretty straightforward. The quote-unquote most difficult part in this case is just figuring out that the exponent, or remembering that the exponent is in excess 127. So you have to take the 127 from the exponents before you do anything. You might be tempted, for example, to add the exponents right away. So you can't really do that because then you'll have incorrect results. So take the 127 first and then align the numbers by either moving the number with the higher exponent to be a lower exponent, or the other way around, the number with the lower exponent to be a higher exponent, and then you can match them, align them, add them, and then convert them back into IEEE format. Multiplication is kind of also similar. We're not going to do a full example of that, but when you multiply two numbers, obviously the multiplication, I'll just explain it briefly without having to go into details. The multiplication, so again, you have the sign bit, you have the exponent bits, you have the Manteja, and then you have another number that has a sign bit, exponent bits, and the Manteja. So the Manteja and the Manteja will get multiplied because those are basically, so you bring back that hidden 1 point, 1 point, or 1 dot the Manteja, you multiply these numbers together, and then for the exponents, you can, the safest way is to remove the excess, add the exponents together, and then add the 127 back. So let's say the first exponent is 5, the second exponent is 6. So you add them together, you get 11, you add 127 to them, and you get 138. Then the sign, negative times negative is, positive times positive is positive, positive times negative is negative, and negative times negative is positive. And then the result gets written down here, and then you normalize it. And then you drop that hidden 1. Then you store the results into your new IEEE format number. I hope this was helpful, and I hope that you know now how to add IEEE floating point numbers. And I hope this makes sense now to when now you read or you see IEEE format numbers that actually understand what's happening and how they're saved in memory and how they're represented and decoded. Thank you for watching.